I'm Yuriy Polyakov, Principal Scientist and VP of Cryptography at Duality Technologies. I'm also a project co-lead for the OpenFHE library. So today I'm going to talk about a new hybrid crypto scheme that together with Andrea Alexandru and Andrei Kim we developed. The name of the talk will be General Functional Bootstrapping using CKKS. I think Andrea is actually joined this call, so she would also be available. The paper itself is published at the ePrint, so the link here is provided, so 1623.
Yuriy,
yes?
Sorry to interrupt you, just to jump in. I don't think you have the screen share.
Oh, okay, sure. Let me share it just 1 second. Okay, and I'm going to present the joint work with Andrea and Andrei, here we will propose a new hybrid crypto scheme, and a paper on this is available on ePrint. And the agenda for today's talk will start with a background on FHE schemes and functional or programmable bootstrapping. So the same name is used interchangeably. Then we will discuss our proposal, hybrid BFE CKKS crypto system, and we'll explain why we chose this hybrid approach. An important component of this is trigonometric Hermite interpolation, which we'll discuss. And we will follow by presenting the CKKS functional bootstrapping algorithm. Afterwards, we'll discuss how one can achieve higher precision using certain multi-precision technique. And we'll conclude by comparison with other methods, and we'll share some concluding remarks. So first, we'll start with some background. And I'll use the, I would say, debatable term of generations. I know not everyone agrees with this term, and it can be a little bit subjective, but it still helps us understand the evolution of FHE schemes, and also it will make it easier to understand why we decided to propose the scheme I'm going to discuss. So the first monumental work was, of course, Gentry's PhD thesis, and that work was presented at the end of 2008 and was published in 2009. This scheme was based on ideal lattices. It introduced somewhat homomorphic encryption scheme, bootstrapping, and also at the time the squashing procedure. And it was the first FHE scheme that was ever presented. Of course, it was slow, 30 minutes per basic operation, but it paved the way for all the major advances that we're seeing now. Another important scheme in this first generation was a scheme by Van Dijk, Gentry, Halevi, and Vaikuntanathan that essentially applied the same Gentry's blueprint, but to the case of an integer problem, so the problem of approximate integer GCD. And the main advantage of that particular scheme was its simplicity. Something that should be kept in mind, of course, is that neither of these schemes are considered practical, and some other schemes are used and implemented in modern libraries. Next, we're going to talk about the second generation, and the second generation, I would say, came from two major works by Zvika Brakersky and Vinod Vaikuntanathan that presented an LW and a ring LW schemes and certain new tools there. And all of these ideas plus some more were incorporated in the BGV scheme. And that's still being used today. And some of the major features of this BGV scheme were realization. Modular switching was added to control the noise and to have essentially more practical schemes even without bootstrapping. And in parallel with this, SIM depacking was introduced and as a way to improve the throughput of these schemes. And there was a monumental work by Smart and Vercauteren that discussed this. Another scheme that's also very popular now is the BFE scheme, which is also a leveled scheme, which is identical in functionality to the BGV scheme, but uses a so-called scale invariant approach, which makes it a little bit easier to use in practice. And this scheme was originally formulated for LW by Zvika Brakersky, and then the RLW variant was developed by Fan and Vercauteren. And other schemes were also developed as essentially other leveled schemes. Many of them are now abandoned because some of them were based on the overstretched n-true assumption. And something to note that these two schemes, BGV and BFE, are still actively used. They're often used without bootstrapping because bootstrapping has been very slow and inefficient compared to the other schemes that we're going to discuss today. However, there is a very interesting new work by Rabin and Frem that supposedly proposes a bootstrapping for BFE that is quite efficient. So it's a new work, so it's hard for me to comment on this, but so far, bootstrapping is rarely used for BGV and BFE. So the third generation, a major component ingredient in that third generation is a scheme by Gentry, Sahai, and Waters, JSW scheme, which featured a couple of interesting new capabilities. So first, to perform homomorphic multiplication, linearization was no longer needed. In addition to that, and related to that, asymmetric noise was allowed. So many multiplications can be done at a small noise cost. By itself, the GSW scheme is rarely used in practice. It's typically an ingredient for some hybrid systems. And a major advance in FHE was developed by Leo Ducam and Daniela Michancho in the scheme that they called FHE. It's also known right now as DM scheme. And this was the first scheme that achieved the bootstrapping latency of less than 1 second. And the features of these schemes, it was a hybrid scheme. So it was a little bit different from the blueprint, from Gentry's blueprint, where essentially the same scheme was used for bootstrapping. Here, the input scheme was additive based on LWE. And for the bootstrapping, a different scheme, ring JSW in this case, was used. And effectively, this was the first instance of functional or programmable bootstrapping. So this scheme supports evaluation of Boolean circuits using techniques that were later extended to larger precision. And the other scheme that was that followed the same blueprint, it's a DDM blueprint, and which is extremely popular now, the often called TFHE scheme, also called CGGI scheme, was introduced subsequently, and this scheme featured more efficient, I would say, smaller bootstrapping key, and it also introduced a different blind rotation accumulator, so that essentially did bootstrapping differently. And I would say the end result of the scheme is that the latency of below 100 milliseconds was achieved. And there were many papers published afterwards, which I know have been presented in this forum, proposing extensions to larger precisions and various techniques based on it, like circuit bootstrapping and so on. The biggest efficiency limitation of this class of schemes is that bootstrapping is done for one number at a time. So although the actual latency is relatively small, when we need to achieve a high throughput, this becomes much more challenging. So now we're going to switch to the 4th generation, and here a major advance was the approximate homomorphic encryption scheme by Cheon, Kim, and Sun. And the main feature of this scheme was the cheap rescaling operation. So the ability to scale down encrypted numbers could be done at the cost of modular switching instead of doing bootstrapping. This scheme supports efficient polynomial evaluation, that is evaluation of polynomial interpolations for many functions. And it has been used a lot for many machine learning applications and applications dealing with real numbers. And later, this bootstrapping for this scheme was added. I mean, I'll put bootstrapping in quotes here because it's slightly different from the Gentry's blueprint, but this bootstrapping capability enabled deep computations. And there is a big advantage that this approach has. It can achieve best bootstrapping throughput among all schemes that we have discussed, but until recently, it has not supported functional or especially general functional bootstrapping. This has been a limitation. And the idea is to, and the research question that we were trying to answer is, okay, so we have this TFHE family of schemes that support general functional bootstrapping and general circuit evaluation. They have these schemes have low latency, but the throughput is 2 or 3 orders of magnitude lower than, let's say, the throughput for the CKKS bootstrapping. Then, on the other hand, we have CKKS, this approximate scheme that can achieve much better throughput, but does not support general functional bootstrapping. And the interesting question is, could we develop a vectorized cryptosystem, so meaning SIMD cryptosystem, that can support both the general functionality of TFHE schemes and still achieve the same SIMD efficiency as CKKS? And our answer, of course, was positive in the paper, and we published the paper. And how did we solve this problem, or what approach did we use and why? Maybe there are a couple of considerations here. First, we liked the DM blueprint of using 2 schemes, a hybrid approach. One scheme is relatively lightweight, so additive scheme. So in the case of DM, that's LWE, we're going to replace it with BFE. And the other scheme that's used for the actual bootstrapping or accumulator is much heavier and does all the main work. And it, of course, supports multiplications and many other things. And in our design, we replaced ring JSW with CKKS, since CKKS has the highest throughput. So this was the design we chose. And again, you can think of BFE here as being an additive scheme. Of course, if needed, multiplications can be added, but it's better to think of it this way. Then we used CKKS for evaluating lookup tables using this functional bootstrapping capability. And we do it in a way that also reduces the noise at the same time. So this is something that's going to be important about this capability, maybe as compared to the classical CKKS bootstrapping, that there is a mechanism to reduce the noise, just like in classical, let's say, Gentry-style bootstrapping. And the main tool that we use for this is Trigonometric Hermite interpolation. We'll have a separate discussion why. This tool is extremely useful. And after we perform this bootstrapping and function evaluation in CKKS, the result is switched back to BFE. And so why we chose this approach? First, this hybrid scheme is exact. So we come back to BFE, and what we decrypt will be an exact result, just like in BFE. So this provides extra immunity for, let's say, INCPAD type of attacks. So this is one motivation. So to make sure that in this case, achieving INCPAD would not require noise flooding. This was one motivation that we had, so that this scheme is exact. The second is the, I would say, the blueprint, the hybrid blueprint is quite useful and also significantly simplifies noise analysis in this case. And because when we come back to BFE, our goal is to make sure that the decryption result is correct. We don't need to track how many, we don't need to additionally consider, okay, how many bits of the actual message have been corrupted by the noise. So I would say simplicity is certainly a major consideration. Plus, moreover, many techniques that were previously developed for hybrid crypto systems such as TFHE and FHE can be readily applied to this construction. So a lot of the toolset could easily be used. And now we're going to talk about the trigonometric Hermite interpolation, which is the essential block of in this scheme. So let's quickly refresh. What is CKKS bootstrapping? CKKS bootstrapping, the main block of bootstrapping, deals with the operation of modular reduction. So when we take a certain small ciphertext, we increase it to a much larger ciphertext, and then we get something like m plus qi, and the goal of the next operation is to remove this qi. And the approach that was proposed in the 2018 Eurocrypt paper was to use a sine wave approximation. And this sine wave approximation had special constraints. For instance, the message itself should be significantly smaller than this q, so that we can use the essentially linear interpolation and achieve high precision. If we look at it at this particular approach from the perspective of, let's say, approximation theory, what we'll see is a very specific example of trigonometric Hermite interpolation. And in this case, we're talking about 1 point trigonometric Hermite interpolation. 1 point meaning that we only work with essentially one period of the function. So because the trigonometric approach will automatically cover all other periods. And in that interval, we choose only 1 point, so near 0. And then we add an Hermite constraint. So what makes it an Hermite interpolation is when we put special constraints on derivatives. So in this case, we put a linear constraint on the derivative, so we can approximate the value close to 0 up to a certain range where the linear function works well. So we have 1 point interpolation. It's done the job for bootstrapping. It has its own limitations, and it does not give us an ability to evaluate a function. So the question that we asked, can we extend this to, let's say, p points, so that we can support essentially mod p lookup table evaluations? And we're going to go step by step to see how we can do that. So first, we can, if we want to go to a p-point trigonometric interpolation, and the input, let's say, is in ZP, and we want the output also to be ZP. So think of P as a plain text modulus here. One could use standard Fourier series, so trigonometric interpolation is sum of sines and cosines, well-known result. And this particular function, nice property is that it already automatically removes the QI term, so it provides the bootstrapping capability. So it also allows us to evaluate functions mod p, so not just at a single point. So we can automatically use the full range in the period, not just a small area, like in the case of CKKS bootstrapping. But by itself, it's not sufficient to solve our problem, because the messages that we're feeding to the bootstrapping and to the trigonometric interpolation are going to have some noise. So if there are BFE messages where most significant part is the message, then we have the least significant part that contains the noise. So we need a mechanism to control this noise, to make sure that this noise, which will increase with CKKS computations, does not reach the message space, does not affect the message itself. And to address the noise issue, we introduce a noise reduction in the interpolation. And the noise reduction in this case means putting an additional constraint or set of constraints on the first derivative at each of those points. So we can set the first derivatives to 0, and making sure that we get quadratic noise reduction as part of evaluating these functions. So mathematically speaking, what we're transitioning from a Lagrangian, from a trigonometric Lagrangian interpolation to trigonometric Hermite interpolation. In this case, that's the method from the mathematical perspective. Of course, the coefficients of this interpolation can be found using a linear solver, but we wanted to develop something that's useful and easy to use and easy for analysis. This is why our goal was to also derive and include analytical expressions using the trigonometric and interpolation theory. And there are some results for more general Hermite interpolations that were published in the 60s, for instance. And we used one of such results for so-called OM trigonometric Hermite interpolation to derive the series that is presented on this slide. And so this is an analytical expression. It's easy. We'll analyze it a little bit closer a little bit later. But something to note immediately is that if we plug in the plaintext modulus of 2 into this interpolation expression, we'll get the well-known function. Well-known meaning this function was used in the Asia Crypt 24 paper, where Boolean arithmetic using CKKS was proposed and developed. This particular function gives us the floor modular function. So it's a very special case for p equals 2. We get a result known from the prior Asia Crypt work. So, of course, this trigonometric series is useful for analysis, but it's not FHE friendly, meaning that we cannot use optimized algorithms to evaluate it efficiently. And so we took an extra step, and we rewrote this trigonometric interpolation in terms of complex exponential function, so that we could get a power series for it, and then we can use our regular power series evaluation methods. And of course, the high-level idea is we write it as complex functions, and then we extract the real part, because the real part is the one that we're focused on. And in this form, looking at this as a power series, it's easy to see that to evaluate a lookup table for a plaintext modulus of p, we need a p-1 degree polynomial, and we can evaluate it using a Peterson-Stockmeyer algorithm, which has complexity of roughly a square root of 2p homomorphic multiplication. So it's we can easily plug in and use this power series evaluation So we went a little bit further because first order derivatives are great. They can reduce the noise, but it was not clear whether this noise reduction would be sufficient for all applications. And we already saw some applications where it's not sufficient. So to take it further, we developed analytical expressions for the second order and third order Hermite interpolation, meaning that the first two derivatives or the first three derivatives were set to 0 at all p points. This we see this as a tool. So this trigonometric Hermite interpolation is a very useful tool that allows us to control the noise. And when we go to the second order interpolation, the increase in the degree is, I would say, relatively modest. I mean, from something like p minus 1, we go to 3p divided by 2. And when we go to third order interpolation, the power series degree grows to 2p minus 1. So one way to think about it is that the cost of going from the first order interpolation to the third order is equivalent to the cost of adding 1 extra bit of precision to the lookup table evaluation. And yes, as I mentioned previously, when we deal with a series of LUTs that we need to evaluate, we saw instances where first order approximation by itself was not sufficient, so we had to use second order approximation. We haven't seen use cases for the third order case yet. And maybe one also interesting question to answer and that we examined as well is, okay, so what we just described is based on is an approach for functional bootstrapping. Alternatively, we could evaluate regular CKKS bootstrapping and then use polynomial Hermite interpolation on top of that. So to achieve the same effect, and how does this approach compare with direct use of functional bootstrapping? And first of all, our analysis shows, and the analysis is presented in the paper, that the degree is double, so which means increased complexity and increased levels, so by 1. Moreover, the classical CKKS bootstrapping, because of this 1-point interpolation, typically requires larger scaling factor because we have to reserve extra room where this 1-point interpolation does not work. So it's like, mathematically speaking, you can interpret this. What is more efficient? A 1-point interpolation followed by, let's say, p-point interpolation, polynomial interpolation, or just doing the p-point interpolation to begin with. And our answer is that in scenarios with bootstrapping, the trigonometric Hermite interpolation, that is the functional bootstrapping approach, will be more efficient. Of course, there are situations where we may not deal with the deep computation, and we may not need bootstrapping. Then, of course, the polynomial Hermite interpolation would be a very reasonable option with a reduced requirement. And something to note also that implicitly, this the specifically polynomial Hermite interpolation was used in prior works, for example, the Bleach work and in earlier work in 20 work. So it's in our opinion, it's important to look at everything we do with CKKS in terms of approximation theory and in terms of this tool, trigonometric Hermite interpolation, and design this tool, fine-tune this tool in a way that allows us to achieve the goals. So now we're going to talk about the actual functional bootstrapping. How do we integrate this trigonometric Hermite interpolation into it? And the first question that deserves attention is the switching from BFE to CKKS, since this is a hybrid scheme. And at a high level, this switch is quite simple. It's more of something we do in our mind and use very cheap operations. So our starting point is BFE encryption or RLWE encryption. We're just using symmetric encryption here for simplicity. And effectively, this RLWE encryption can be interpreted just directly in our mind as a CKKS encryption using the coefficient decoding. This is something that's important. Both BFE and CKKS in this case are used in the coefficient encoding, not in the packed or slot encoding. And so it's essentially in our minds, we interpret it this way. And something to keep in mind when we take the BFE message, we put it into CKKS, we also include the noise, the BFE noise, into this message. And this is why when we perform the evaluation, this noise may grow due to CKKS computations, and we need to control this noise using the derivatives, essentially, first order or maybe or second derivative. So effectively, the process of switching from BFE to CKKS and back does not require any work with key material, so it's cheaper than key switching, let's say, in TFHE style schemes. All we have to do is something like modular switching and scaling to adjust the moduli, so let's say between power of 2 and NTT moduli, but these are this switching here is, I would say, trivial. And now we're going to look at the actual CKKS functional bootstrapping algorithm, so the way we present it. And although we have here essentially 8 steps that describe it, we're going to focus only on the bootstrapping step, because everything else is just related. Let's say steps 2 and 3 and 8 are related to this very simple switching from BFE to CKKS. And what we have as the main block is CKKS bootstrapping. So what we've seen in many works, and for instance, it's the standard 4-step protocol. Sometimes the order of this is switched, but at a high level, we do mod raise to go from a smaller modulus to a higher modulus, where we get an overflow term. Then, since we're in a coefficient encoding at this point, we have to apply a linear transform to go from coefficient to slot encoding, so we can evaluate functions. Afterwards, we perform the actual LUT evaluation, which is in our case is replaces eval mod that's used in classical CKKS bootstrapping. And finally, after we're done with the computation, we need to put it back into the coefficient representation. We call slot to coefficient transformation to basically make it ready for BFE afterwards via scheme switching. So we also want to note a couple of important, I would say, properties that this algorithm supports different and arbitrary input and output plaintext moduli, just like TFHE family. So no restrictions on the plaintext moduli, because quite a few algorithms often have restrictions. In this case, we have the same generality as TFHE. Also, if we, in addition to the functional bootstrapping, we want to evaluate some, let's say, polynomial function or some rotations or whatever, one approach is to reserve more levels in CKKS. So as soon as we're done with eval LUT, we can do some extra work, like a leveled computation after that. So this is readily available at the cost of, let's say, increasing levels. And something else to note, this is in contrast to the TFHE family, is that only one functional bootstrapping operation is needed here. We don't need it for arbitrary LUT computation. We don't need 2 bootstrapping operations, as in the case of the TFHE family. There we have certain negacyclic requirement, the most significant bit. No such issue here. We directly evaluate the function, so we get essentially 2x improvement in this case. And next, we'll briefly look at some experimental results. So these results were implemented in OpenFHE. They are single-threaded, and very briefly, let me go through this. So log P is the log of the plaintext modulus. So we went here up to 12-bit plaintext moduli. So this is more of an internal parameter, but it's related to the scaling factor and what we use for each level. Here we're presenting the essentially ring dimension, so 2 to the power 15 for the first case, 2 to the power of 16 for most of the other cases. Note that we chose the parameters in a way to maximize throughput. If our goal was to minimize latency, we could probably fine-tune this a little bit more and do more work with 2 to the power 15. And so we're also listing, of course, the moduli that were used here, and now the analysis of the actual runtimes. So one important result is that the amortized time, so amortized time meaning the time of bootstrapping divided by the number of slots. And the number of slots in this case is the ring dimension. So it's like, think of it as a BFE ciphertext. Is, let's say, even for 8 bits of precision, we're under 1 millisecond, which certainly is better than any prior results. And the latency here, of course, is more significant. So it's clearly higher than in the case of the TFHE family. So for instance, for this 8-bit case, it could be 49 seconds here. However, this approach is easily parallelizable. So the runtimes we're looking at here are for a single core, and we can do, let's say, 64,000 numbers at a time. And let's say if we have a 16-core machine, we can achieve roughly the same latency times for 1 million numbers on that 16-core machine. So, of course, we saw in this table that the cost grows as we increase the precision. So similarly to TFHE, although it's the increase is much, I would say, is not as fast as in the case of TFHE family schemes, because at a certain point we have to double for every extra plaintext modules, we have to double the ring dimension. Here the cost is much cost increase is much gradual. So to accommodate this and to support, let's say, 32-bit arithmetic, so something that is of interest and is often done in the basically for TFHE, we introduced similar tool set that was developed for a few TFHE family of schemes to this approach. I mean, of course, there are quite a few changes, but the blueprint is going to be very similar. So first, we need some auxiliary functions to develop this multi-precision toolset, and 2 such functions are modular reduction, and we have a very nice analytical expression for this function that we also include in the paper. And then the other is the step functions. Using those 2 functions, for instance, we can do multi-precision sign evaluation. We can also, these functions will give us tools to evaluate a more general LET. So as an example of multi-precision sign evaluation, so we here we're effectively adopted the blueprint in a prior AsiaCrypt paper of how does one support large precision sign evaluation, and it's going digit by digit, where there is an operation of a homomorphic floor that has to be executed for each digit, and then at the end we essentially evaluate the most significant bit operation. So very similar design. So we have a homomorphic floor function. One major difference here is that it requires 1 bootstrapping, as I previously mentioned, not 2 bootstrapping operations, as in the case of TFHE. Second, we apply very similar blueprint where we're going digit by digit, and then at the end, we're evaluating the MSP. So the same functionality, the same linear scaling when support for larger precision is needed. And we also discussed how one can evaluate multi-precision LUTs. So more general, not just functions like sign evaluation. And first, of course, we introduced homomorphic digit decomposition as using this the prior R mod function. It's the both chained and tree-based methods that are used in the TFHE case can be applied here for to build larger LUTs. And our method, so something to note, one of the properties of few TFHE is that they support multi-value bootstrapping. So if we need to evaluate multiple LUTs on the same ciphertext, significant optimizations can be used. So heavy part can be reused. Same is the case here. So we can compute the important terms of this power series once, and then just do the final step of Peterson, let's say Peterson-Stockmeyer or some other algorithm to do the polynomial evaluation. Also, something that's needed in the tree-based method is support for encrypted LUTs. So not when LUTs themselves are essentially ciphertext. This capability is also supported by the method. It's just what it means is that some of the coefficients that we have in the interpolation, instead of being plain text scalars, they become encrypted. So, so in this case, something like baby step, giant step method could be used to evaluate those encrypted LUTs. So effectively, the tool set for an LUT evaluation using tree-based method is available. And the simple story is that as far as we've seen so far, any multi-precision techniques that have been used for TFHE should be available in this case as well. And we'll briefly look at the experimental results for sign evaluation. And so here, maybe the trade-off is that we wanted to support 12-bit, 21-bit, and 32-bit sign bit evaluation, and we varied the digit size, starting from working with bits up to a larger number, and giving various trade-offs. So there is always a benefit of using larger digits, but up to a certain extent, because we saw that the cost of each digit increases. And maybe I'll the notation is very similar to the previous case. What I would like to just highlight is large P is the full plaintext modulus, and small p is the plaintext modulus for the digit. The rest is quite similar. And let's look at one number in particular. So for 32-bit sign evaluation, we using 4 8-bit digits, we would expect a latency of roughly over 3 minutes for, again, single-threaded execution, and with amortized time of 3 milliseconds. So this is something that we got for our proof of concept implementation in OpenFHE. And all these results are for the case of the ring dimension 2 to the power of 16. So brief comparison and then concluding remarks. So how does this method compare with the essentially TFHE family? So for 8-bit LUTs, we see about 3 orders of improvement in the throughput than the TFHE approach. Of course, yeah, something to note that if we look at smaller precision, this gets closer to 2 orders of magnitude. So because the way the CKKS-based approach scales is, I would say, more graceful for larger precisions than the TFHE one. Also, we compared the runtimes for multi-precision sign evaluation with the prior OpenFHE implementation. It was published in the AsiaCrypt paper, and we see roughly 3 orders of magnitude improvement there. We compared this approach with another amortized approach that was recently proposed in Asia Crypt 23 and 24 that uses BFE, which has some it's a functional bootstrapping method with, I would say, a little bit more constraints than in our case, let's say for the plaintext modulus. And what we see is that our method is more efficient. We explain in the paper why, even because the degree of the polynomial that needs to be evaluated is much lower. And for the case of 8-bit LUT evaluation in a comparable implementation, we also implemented this method in OpenFHE. We're seeing something like on the order of 6x. And we also compared the runtimes of LUT evaluation with publicly available results based on TFHE circuit bootstrapping. And there we saw roughly 2 orders of magnitude improvement. Something to note, again, although we did not do this in the paper, from what we could see, all the tools that are used in circuit bootstrapping could be adopted for this approach. So concluding remarks, our CKKS method is more efficient than TFHE when the number of slots reaches the order of thousands or even hundreds. So this is more for larger precision cases. Certainly, batch processing applications where the main focus is on working with large data sets, like, for example, encrypted SQL. So will benefit the most because there the main goal is to achieve the highest throughput. And although we focused in our work on the hybrid BFE CKKS crypto system, one can develop a full end-to-end CKKS solution. And there are some concurrent works that essentially work in this direction. We also presented some initial algorithmic description for that case. So this is possible to effectively have a full end-to-end CKKS implementation. The noise estimation would have to be done a little bit more careful in this case. And various generalizations of this approach are possible. For instance, the work that supports multiple independent LUT evaluations, that approach can be adopted here as well. And something to note is that the runtimes for this proof of concept are for a proof of concept implementation, something that we quickly put together. Of course, many optimizations are possible, and these numbers can be improved. So we think it's a new exciting era, so that we can that could be based on this functional bootstrapping method, and our current plan is to make the public version of this available around May in OpenFHE. And so this concludes my talk, and I'm ready to take questions.